Welcome once again, dear students, to another video lecture. So, in the last Matlab video lecture, I have given you the basic framework or basic uh, interface of Matlab, how to access Matlab online, and also I have given a brief idea of how to generate a signal using Matlab. In particular, I have used a unit impulse signal as an example. So in this particular video, uh, your friends or my students will help you in understanding how to generate the rest of the fundamental signals, elementary signals that we have studied. It includes unit step signal. So Krishnapriya will help you in that. Then after unit step, you have unit RAM signal. So you know what is a RAM signal. So Fida will help you in that. The third elementary signal is a unit parabolic signal. So Kevin will help you in that particular thing. Then the sinusoidal signal is explained in detail by Anandhu, and real exponential signal by Muhammed Salmun. So at the outset, let me thank each of the student who voluntarily took this as a challenge, and they have completed this tutorial. So let me hand over the baton to Krishnapriya, and she will help you in understanding more about unit step signal, and then the rest of the team members will take up. So let me hand over to unit step signal.
Hi all, myself Krishnapriya and I'm here to explain you about how to plot one of the elementary signals, that is unit step signal, using Matlab. Hope you all know about analytical representation of unit step signal. The output of the unit step signal will be 0 for the time instance less than 0 and will be 1 for values greater than or equal to 0. You all know about how the graphical representation of unit step function will be. Here we are going to plot the graph using Matlab. Here I am using the online Matlab. I think all of you are now aware about the command window and the workspace, right? Okay, here I am taking a new script for writing the commands for obtaining my graph. So like in the previous cases, the first two codes will be clear and CLC for clearing the command window and workspace. First, I am giving a title of what I am going to plot. So here I am going to plot the unit step function. Here I used a percentage symbol just to make it a command line so that it will not be executed. Here we can consider two cases of unit step signal, that is in discrete time case and continuous time case. First, I am going for discrete time signal. Initially, we have to give the time interval, that is from where to where in x-axis we need the output signal. So here I am giving the variable n, which denotes the time instance along the x-axis. So n is equal to, within the square brackets, just like in case of range, first we have to give the starting point. Here I am taking the starting point as minus 15. Then I'm giving a colon between the values. So my next value will be the spacing. That is the spacing value between two adjacent instants. Here I'm taking it as 1 against colon, and then my final value 15. To know the values assigned to n, we can just simply run the file. So before running the file, we have to save the file. So here I'm giving the name as unit step signal. So in the command window here, you can see the values assigned to the variable n. That it ranges from minus 15 to 15. So we assign the interval, time interval, along the x-axis. that we need to plot along the x-axis. And after the command, I'm giving a semicolon so that it will not be executed along with the next line. So next, we have to give the command for obtaining the output signal. Before that, you have to just imagine what will be the output signal and how the graph will be. We have already discussed that the output of the signal will be 0 for instance less than 0 and will be 1 for instance greater than or equal to 0. Here we are taking the instant from minus 15 to 15. So how many instants do we have? We can find it from the workspace. Here the dimension of the variable variable n is 1 by 31. That is, it have the dimension of n is 31, 1 by 31. That is, it have 31 instance, of which the 15 instance will be from 15 instance from minus 15 to minus 1, and the 16 instance are from 0 to 15. So how many zeros and ones do we have in the output line, in the output graph? We only need output as 0 up to minus 1, and after that we need value as 1. Therefore, number of zeros will be 15 and number of ones will be 16. So we can give the command for obtaining the output signal as the variable u of n. U of n is equal to, within the square brackets, first we have to give how many zeros we need. So I'm giving zeros within the parenthesis. In Matlab, we are giving values just like in matrix. So here I'm giving the number of zeros as 1, 15, so that I can obtain 15 zeros within a row. And 1 and 15 represents the rows and columns respectively. And next I have to give ones. So I need 16 ones. So here we give the command for obtaining the output of the signal. So next we have to plot the graph. For discrete cases, we are using the command stem. So we are giving the command stem, and within the parenthesis, first we have to write which variable do we need to obtain along the x-axis. So here I need n along my variable n along the x-axis and the output u of n along the y-axis. So I gave the output, and before that I'm giving the semicolon. So here I gave the command for obtaining the graph. Then I can obtain the graph by running the file. So I pressed F5. So you can all see we obtained a graph of discrete time signal, and from the graph it is clear that we obtained the graph from minus 15 to 15, and the value of the signal from minus 15 to 1 is 0, and from 0 to 15 the value is 1. So we obtained the graphical representation of discrete time signal. Next, we have to specify the x-axis, y-axis, title, etc. of the graph. So here for that I am using the commands title within the single inverted comma, unit step discrete, and x label. What I am having in my x-axis, n, then y label. It is amplitude. Next, to limit the range of x-axis and y-axis to see the graph clearly and accurately, I'm giving the command axis It is first we have to give from where to where we need the x-axis in the graph. That is, I'm giving from minus 20 to 20. Next, I have to give from where to where I need the value of y-axis in the graph. So I'm giving from minus 0.2 to 1.2. Now we can run the file. Here, now the graph is more clear. That is, we have given the title of the graph and we have labeled the y-axis and x-axis, and it is clear that we have obtained the output signal from minus 15 to 15 and minus 15 to 1. We have obtained the output as 0, and from 0 to 15 we have obtained 1 as our output signal. Okay, now we have completed the discrete time signal. Next, we have to plot the continuous time signal. So next, continuous time signal. Okay, in the similar way, we can give the commands. First of all, we have to give the time intervals. So here I'm giving the time interval with very small spacing between the two time instants so that we can obtain like a continuous signal. So here I'm taking the variable t which have the values from minus 15 to 15 with a small spacing between the instants. So I'm giving within the square brackets my starting point minus 15, and I'm giving a very small spacing that is of 0.1 and my final value 15. So here we have given the time instance. That next we have to give the command for obtaining the output signal. Similarly, like before, we have a total before that to know what values are assigned to t, we can run the file. So here you can see in the command window, we can see in the command window what values are assigned to the variable t, and it's from minus 15 to minus 15, minus 14.9 to 15. So how many instances do we have? We have can find it from the workspace. The variable t have one dimension 1 by 301, that is it have 301 time instance, of which 150 will be 0 and 151 will be 1. That is from minus 15 to minus 0.1. Minus 0.1 will be zeros, and from 0 to 15 it will be 1. So we can give the command for output signal as u of t is equal to, within the square brackets, zeros. How many zeros do we have? 150. And ones, how many ones do we have? 151. So we have given the command for obtaining the output output signal. So next we have to give the command for obtaining the obtaining the graph. Okay, in continuous cases we are using the command plot for obtaining the graph. So here I'm giving the command plot. Like in the previous case, first we have to give what we need in the x-axis. I need the time t in the x-axis and the output u of t in the y-axis. So here I given the command for obtaining my graph, and next I can run the file. So here I obtained the graph, and it can be seen that from minus 15 to 0, minus 15 to minus 0.1, it's not in 0. So minus 15 to minus 0.1, the value is 0, and from 0 we can clearly see a slight slanting, that is from 0 its value is 1. From 0 to 15 its value is 1. So in order to have a spacing, specifying the x-axis, y-axis, and to give a title, and finally to limit the x-axis and y-axis, we can use the commands that we given earlier, that is title, x label, y label, and axis. We can copy and paste here. Title become continuous, x label t, and y label will also y label will be amplitude, and from x-axis we can give minus 20 to 20, and from y-axis we can give minus 0.2 to 1.2, and finally we can run the file. So here you can see clearly minus 15 to minus 0.1, it's not in 0. There is a slight slanting for the line. From 0 it is 1, and before 0, that is minus 0.1, which is closely near to 0, it is the value is 0, and from 0 to 15 the value is 1. So here we obtain the graph for unit step signal, both in discrete and continuous cases. To obtain the graphs together for analysis, we can use the command figure. So before stem, I'm here giving the command figure. Within the parenthesis, I'm giving within the C bracket, I'm giving 1. And here before plot, I'm giving figure 2. So after running the program, we can obtain 2 figures. Like my first figure will be in discrete time signal, and my second figure will be continuous time signal. Okay, hope it is clear for all, and thank you.
Good day to all. In this tutorial session, I will be discussing on how we can generate a unit ramp signal in Matlab. So let's move on to our Matlab window. Right. So firstly, I have saved my file name as unitRampSignal.m. We can now give our clear and CLC inputs. Right. So the workspace and the command window is cleared. Now, what you're going to do is you're going to generate a unit ramp signal. We can just give the title as generating a unit ramp signal. And now here we're going to consider 2 main cases, the first one being the discrete case and the second one being the continuous case. Right. Now for both the cases, we're going to generate the ramp signal from a unit step signal. So as we know, in the discrete case, R of n is equal to n times u of n, and for the continuous case, R of t is equal to t times u of t. So for the discrete case, first of all, we can just assign values of n. So let it be from minus 10 to 10 with a space of 1. So here the n values will range from minus 10, minus 9, minus 8, etc. up to 8, 9, 10. So now that's with the values of n. Now let's just give the number of zeros and ones, because for a unit step signal, when n is greater than or equal to 0, the value is 1, and for when n is less than 0, the value is 0. So we can just give values of zeros and ones. So for u of n is equal to zeros for when n ranges from minus 10 to 10, we'll be having 10 zeros and 11 ones. So we can just give 10 zeros and 11 ones, right? Yeah. So now we have given. Now good. Now what we have to do next is, we know that R of n is equal to n times u of n. Now this is what you have to give next. So we can just give R of n is equal to n dot star u of n, right? So now we have given this command. So make sure that you give a dot here. So that's very important when you run the command. If not, you will not be getting the output properly. So R of n is equal to n dot star u of n. That means R of n is equal to n times u of n. Now what you have to do is, you can generate the graph directly. So for generating the graph, you have to use a stem command. And in the stem command, you can give x and y values. And for x here, we have n, and our y value is R of n. Right. Now, another important thing that I'd like to say is that these two lines, that n is equal to minus 10 to 1, and the line that you give for u of n, are not to be printed in the output. So you don't need it as your output. So you can just give a semicolon there so that it doesn't come out as your output. You don't even need this also as your output. We just need the graph. So now if you give stem n comma R of n, you get the graph. Now we can just run it and see. Now we have obtained a graph. I'll just let you see the graph also. So okay, now hope you can see the graph now. So this is a graph that you obtain. Now if you look into the graph, there is no x label, there is no y label, and neither are the axis defined. Now this is just an axis that is given on a default node. So we can also assign the x label, y label, and the axis labels. So we can just close this one. Yes, now I can just show you how we can give the x label and y label. We can just give x label, and here we can give the x label as discrete values n, right? And you can give the y labels as well. You can give it as amplitude, right? Good. Now we can give the axis. Let the axis go from minus 10 to 10. Minus 10 to 10. Now these two are the x-axis values, and the next two that we give will be for the y-axis. So we can just give minus 5 to 10 as the y-axis, right? Good. Now we have the axis values as well. Now if you run it, you can very well see that you have your x label and y label. We can just see running it. Now I'll show you what we have obtained. Now you can see the difference that you have. Here you have the x label as discrete values n, and here you have the y label as amplitude, and then the axis also is also defined from -10 to 10 in the x-axis and -10 to 10 in the y-axis. So that's with generating the discrete unit ramp signal. Now I'll just close this window. Now we can move on to the rest. We can now generate the unit ramp signal in the continuous case. Now for the continuous case, the only difference is that you're going to consider that t instead of n, and the values will be given the same, but we can change it into a continuous case. So we can just paste this as the same. Now if you look, we can give t here, the range, let's keep it as -10 to 10, but let's give the space as 0.1, as it is a continuous signal, but let's just give it as 0.1. Now we can just assign the same as we in the continuous case. We can just give the same for the unit step signal. So here we have the number of zeros will be varied because in the discrete case we had given it as 1 as a space between -10 and 10, but here it is 0.1, so hence you'll be having about 100 zeros and 101 ones. So u of n is like that. Now we have t, so sorry, here you should give u of t instead of u of n. So make sure all the n is turned to t when it comes into the continuous case, if you are copy pasting the same. Now another thing is this line also remains the same, as r of t is equal to t times u of t. So you can just copy paste this also here and change all the n to t, right? So t, and this n should also be turned to t, right? So now you have r of t is equal to t times u of t. So these are the equations. This is the equation that is there for the continuous case of a unit ramp signal. So we have this. Now instead of giving stem for stem command for generating a graph, here it is better to use plot. Okay, now in plot again you can give the x and y values. So let's give here you have to give t and r of t. Okay, you can give t and r of t. And so another thing that you have to be careful is that make sure you give the semicolon. If not, all these will be printed in your output. So you don't need this as your output, you just need the graph as your output. So it is better that you give the semicolons here. So now you can plot it as t r of t. Now where t is x-axis and r of t is the y-axis. Now after this, as we did before, we can give the x label and y label. You can just give the same here. I'm not writing it again. Let's just copy paste it and we can just change it. So instead of discrete values, we can give it as continuous values, and here it remains as, this is t here, yes, and this remains as amplitude. Now we can also fix the axis values. So let's give it as we can give -10 to 10 for the x-axis, and let's give -0.1 to 1.2. Okay, hope this is good, right? So we have given all the values, we have given all the programs, we have entered all of them, and now we can see whether this is right. Okay, hopefully this is right. Now let's just run it and see whether there are no other errors. So make sure all the n is turned to t, because without that you won't be getting the graph properly. So make sure there are no n's in the continuous case. Right, now we have a program. So now another thing I'd like to say is, before, if you want both the graph, if you want to see both the graph together, I prefer you to just give figure 1 and figure 2 so that I can show you both the graph together. So I've given figure 1 here before stem command, and here before plot command I'm going to give figure 2, right? So now you have both of them. Now let's run it and see. Now if you run it, you will get two graphs. I'll just show you both the graphs that you get. So this is what you get in the discrete case, and I'll show you the one that you get in the continuous case as well. Now you can see we have both the graphs obtained. So now this one is for the discrete case and this one is for the continuous case, and hence we have obtained the unit ramp signal in both the discrete case and the continuous case. So that's all with the tutorial session on unit ramp signal. Thank you. Thanks a lot.
Hello friends, hope you guys are clear with the unit step signal and unit ramp signal by now. Now we will look on to unit parabolic signal, and unit parabolic signal is one of the standard signals that we use in signals and systems course. And let us try to understand and plot the graph on Matlab. So let us now move on to the definition of parabolic signal. So parabolic signal is defined as a t square by 2 for t greater than or equal to 0 and 0 for t less than 0. The a is actually a scaling factor, and when this a becomes 1, the parabolic signal is called unit parabolic signal. The graph depicts the continuous time case of unit parabolic signal for, and here over, for cases where t is greater than or equal to 0, the graph follows the path of a parabolic function, and for t less than 0, the graph always lies on the x-axis. This is the case of a continuous time case for unit parabolic signal. And the physical significance of the parabolic signal is that it mimics the constant acceleration characteristic of actual input signal. Say, having said that, let us now look into the discrete time case of parabolic signal. The discrete time case of parabolic signal is as shown below. Here we can see that the graph is plotted only at certain discrete points of interval n. For n greater than or equal to 0, the graph will be plotted according to n square by 2, since this is a discrete time case, and for n less than 0, the graph will always be lying on the x-axis. So having said the both continuous parabolic signal and discrete parabolic signal, let us now try to plot these two graphs on using Matlab. So now we have the Matlab online version over here, and in order, first let us consider the discrete time case. So in order to, our ultimate aim is to plot the graphs, right? Graph of two cases, discrete time case and continuous time case. So in order to plot these two graphs, first of all, we need to define from where to where we have to draw our graph. We need to have the points. We need to have the points from which we will plot the graph. So for discrete time case, we are going to define it as m equals minus 10 with an increment of 1 to 10. And what this line of code means is that the graph will be plotted from minus 10 to plus 10 with an increment of 1. That is, the graph will be plotted using minus 10, minus 9, minus 8, etc. up to 0, and 1, 2, 3, etc. up to 10. So having established our points that we have to plot, now we need to define our function, or we need to define our signal. So in order to define our signal, we take the concept of unit step signal, because we have studied that unit parabolic signal is actually the double integral of unit step signal. using that concept, we can define our unit parabolic signal over here. So in order to do that, let us first define our unit step signal. So I am defining my unit step signal as unit step equals zeros. One, we need a zero vector from 1 to 10 and a ones vector, ones column vector from 1 to 11. Now we have defined our unit step vector, unit step function. So now using this, we can define our parabolic function with our definition. So now it will become, since it is discrete time case, it will be n dot raised to 2 dot divided by 2 dot is n square by 2 times the unit step. So now we have defined our unit parabolic function or signal. So now we need to plot the figure. Since now we have finished describing our for now here we have given our points to be plotted from n equal to minus 10 to 10. We have defined our function using unit step and parabolic function. Now we need to plot the graph. So in order to plot the graph, let us write figure 1. So let it be a figure 1. And since it is discrete case, we will give the command as stem, comma our in order to plot the graph we need two axis, which is n and para over here, and we need the title. I will let us for the moment give it as discrete parabolic signal, discrete parabolic signal. And now we need to give the x label. X label will be n and y label will be amplitude over here, amplitude. And now we have to define the axis. So sorry, now we have to define the axis. So in order to define the axis, what axis really means is that from here, when we look at over here, we have defined the n should be coming from minus 10 to 10. That means our graph should be consisting of the points from, or the graph should be plotted among the points from the points minus 10 to plus 10, right? On the axis, what really means is that axis limits the graph portion which we want to see, or the graph portion which we want to be plotted the graph. Either it can be including the minus 10 or 10 part, or excluding the minus 10 or 10 part, and here we will give it as minus 15 and plus 15 for x-axis, and 0 to say 60 for y-axis. So having done that, we have finished defining our points, which is from n equal to minus 10 to 10. We have defined our function using unit step and parabolic function. We have defined our graph plotting requirements. Figure 1, stem, title, we have given title, x label, y label, and axis. So now we have finished our discrete time case for unit parabolic signal. The same is the case for continuous time case, except with some minor adjustment, but the same steps are to be followed. So following the same steps, we will give as, since it is continuous time case, we will give as t equals um, minus 10, 0.1, and 10. As you can see, I have given the increment as 0.1 over here, because as the increment gets more and more smaller, the more precise or the more continuous our graph will be. So I have given 0.1, and now defining our unit step signal. Unit step signal will be zeros over, we need a 0 column vector of 1 comma 100, since the increment is 0.1, and ones vector of 1 comma 101, and our parabolic function will be para. Now it will be t dot raised to 2 dot star 2 dot times the unit step signal. Now we have finished defining our points and our function. Now we need to define our graph plotting. So figure 2, and it will be plot over here since it is continuous time keys, and it will be t comma para, and title, the title part and x label axis, which are all very similar. So there are only the discrete will change it as continuous. So continuous time signal, that now it will be continuous time signal, and the x label will now change as t, and the amplitude will remain the same. So now we have finished our continuous time keys also. Hope you guys are clear with the code. Now let us try running this program. We are having an error over here at line number 9. Let us look into it. Line number 9, para, unit step zeros, para equal to n dot, it's actually unit step, right? Yeah, unit step. So let us now try it again. We're having an error again. Unit step to stop. Yeah, looks like we have to give a semicolon up over. No, we have to give a colon up over here. So giving the colon over here, it will be. Now let us try to run the code. So now we have the discrete parabolic signal, which ranges from -10 to 10, and we have the continuous parabolic signal which ranges from -10 to 10. So we will look into detail on both of it. So discrete time keys. So this is the discrete parabolic signal curve or figure, and this is the code of it. So we have defined, as you can see, we have defined, if you look at the cursor point, we have defined our function to be plotted from -10 to 10 with an increment of 1. So in the graph, we can see that the graph is being plotted from -10 to 10 with an increment on 1. So it will be like -10 plus 1 is -9. So the next point plotted is over -9 and -8, -7, -6, -5, and up over here it will move up until +10. So this is how the points are being plotted, and the unit step function is being defined, and the parabolic function n square by 2 star unit step. So after 0 it follows the parabolic function, and before 0 it follows the 0, and the amplitude has been defined on the y-axis, which is the y label amplitude, and the x label has been defined as n, which is the x label over here, and we have the title as discrete parabolic signal given over discrete parabolic signal over here. And coming to the axis part, it is being given that -15 to 15, 0 and 60. So you can see that our graph is actually showing from -15 to +15, and over the x-axis, and over the y-axis it is showing from 0 to 60. So this is what the axis means. So it can either be a small part of this graph or a larger portion of the graph. So this is actually the use of axis. Now let us look into the continuous parabolic signal. Over the continuous parabolic signal, we have defined our range from -10 to +10, which is from -10 to +10, in which the curve has been plotted, and our increment is 0.1. So on each increment of 0.1, which means minus 9.9, minus 9.8, etc. up to, as you can see, it's minus 7.5 comma y0 over here, and up to until 10 with an increment of 0.1, the graph has been plotted, and the y-axis is being given as amplitude and the x-axis is given as t over here, and the title is being given as continuous parabolic signal. I hope you guys are clear with this unit parabolic signal plotting, and the both cases, discrete time case and continuous time case, only have slight variations, especially on the stem part on discrete time case, and on the plot part on the continuous time case. These two things are the main difference that comes in the two time cases of unit parabolic signal. I hope you guys are clear with it. Thank you.
Hello friends, in this video I will show you how to generate a sinusoidal signal using Matlab. We have two cases, one is a discrete time case and another one is a continuous time case. So let's generate a sinusoidal signal in discrete time case first. For that we want to define the independent variable first. Here the independent variable is discrete time instances. Let's define it as vector n with the minimum value minus 10, has a spacing of 1 and a maximum value 10. Next we want to define the amplitude. A sinusoidal signal in a discrete time case is represented as x of n is equal to a sine capital omega n plus phi, or a cos capital omega n plus phi, where a is the amplitude, capital omega is the angular frequency, and phi is the phase angle in radians. So let's define it as x underscore n is equal to sine of n. For producing a sinusoidal signal in a Matlab, we use the function sin sin itself. Next, we want to plot the discrete time signal. In order to plot the discrete time signal, we use the Matlab command stem. Here the x-axis is discrete time instances n and y-axis is x underscore n. Next, let's give a title to the graph as sinusoidal signal in discrete time. Next, x label as n, y label as amplitude, and next we want to define the range of axis. Minimum value of x-axis is minus 10, maximum value is 10. Minimum value of y-axis is minus 3, maximum value is 3. So let's run the code and observe how the graph will look like. So the sinusoidal signal in a discrete time domain will look like this. It will plot t of minus 10, t of minus 9, t of minus 8 up to t of 10. The time period between these two instances is known as a sampling period. Let's decrease the sampling period and look at how the graph will look like. For that I am going to change this 1 to 0.5 and run the code. Now let's observe how the graph will look like if we decrease the sampling period. Now we get more number of points, and now it will look like a sine wave. Okay, this sinusoidal signal has an amplitude of 1, angular frequency of unity, and phase angle is 0. Let's produce 4 different sinusoidal signals and uh, observe how amplitude, phase angle, and uh, angular frequency will affect the signal. For that, I am going to copy paste this program 4 times. Defining x1 is equal to sine of n. In previous case, same as that of the previous case, here x1, this as x2, and multiplying this signal with 2. Now the amplitude of this signal becomes 2. Then changing the name of the title of the graph to change in amplitude. Now defining this as x3 and giving a angular frequency of pi by 2, making this as x3 and changing the title to change in angular frequency. Changing this to x4 underscore n is equal to sine n plus pi by 2 radians. Changing these to x4 and changing the title to change in phase angle. For getting the graph, 4 graphs in a single window, let's define the function subplot. In this, subplot of number of rows is 2, number of columns is 2, and priority of this graph is 1. Next here, but here the priority is 2. Copy pasting it here, and here the priority is 3. Here the priority is 4. Now let's run the code and observe how the 4 graphs will look like. So this is how the initial standard sinusoidal signal in a discrete time will look like as in the previous case, but a change in amplitude is seen in this graph. That is, the amplitude is increased from initially there is a 1, it is 1, now it is increased to 2. So the amplitude, this is how the amplitude will affect the signal. And the change in angular frequency, when we change angular frequency here, the when I increase the angular frequency here, the time period will decreases. Time period, that is the time taken for completing one complete cycle, decreases. This is how the signal will look like when it undergoes a change in phase angle. When phase angle changes, the signal undergoes a phase shift. Here also you can see a phase shift, but in case of change in amplitude, the phase of the signal doesn't changes. But okay, but in other two cases, it will change the it will make a phase shift in the signal. This is how amplitude, angular frequency, and phase angle affect the sinusoidal signal. Next, let's produce the sinusoidal signal in continuous time domain. The generation of sinusoidal signal in continuous time domain is similar to that of the generation of sinusoidal signal in a discrete time domain. But the difference is that here the spacing of the x-axis is to be reduced, and you want to use plot command instead of stem command. So let's define the independent variable as a vector t whose value varies from -10 with a spacing of 0.1 to 10. The representation of a sinusoidal signal in continuous time domain is x of t is equal to a sine omega t plus phi, or a cos small omega t plus phi, where a is the amplitude, omega is the angular frequency in radians per second, and phi is the uh, phase angle in radians. So let's define it as x underscore t is equal to sine of t. In order to generate the sinusoidal signal in continuous time domain, we use the function plot. X-axis is t and y-axis is x underscore t. Then let's give the title as sinusoidal signal in continuous time. Next, x label as t and y label as amplitude. Next, we can define the region of axis. X-axis varies from -10 to 10, and y-axis varies from -3 to 3. Now let's run the code and look how the graph will look like. So this is how the sinusoidal signal in continuous time signal will look like, and how it has to be produced. Here you can see that in the signal has an amplitude of 1, angular frequency is unity, and phase angle is 0. Another way to represent a sinusoidal signal is x of t is equal to a cos omega t plus phi. Let's define that also. Let's define x2 underscore t is equal to cos of t. Let's change these to x1 of t, and I am going to plot the two functions in the same graph. The syntax for that is plot x1 y1 then x2 y2. Here the x-axis is represented by time and y-axis is represented by x1 of t, and in the second case it is x-axis is time and y-axis is x2 underscore t. Here I use another function known as legend. I will show you why I use this function after running the code. So now let's run the code and observe how the graph will look like. So here we will get the cosine representation and sine representation of the sinusoidal signal. I use the function or command legend in order to get these things. That is here the blue represent x1 of t and red represent x2 of t. That is x1 of t. In the command we have defined x1 of t as a sine t and x2 of t as cos t. So in the graph we will get x1 of t. That is the sine function. This is a cosine function. Then let's see what is the relationship between sine and cosine function. Here I am going to give a phase shift of plus pi by 2. And when I run it, you can here see that the x1 of t is under x2 of t. That why it is not visible here. For understanding, I will increase the amplitude of x1 of t. Then you can see that initially it was not there because it is under x2 of t. Now I increase the amplitude, you can see x1 of t and x2 of t. From this we can conclude that sine of t plus pi by 2 is equal to cos of t. That you know. Next let's do the time reversal on the cosine function. For that I convert this function to cosine function. x1 of t is equal to cos t and s2 of t is equal to cos minus t. When we run the simulation, when we run the command, we get the signal. That is here the x1 of t is under x2 of t. That's why we can't see it. From this we can conclude that when we subjected a cosine function in time reversal, we get the cosine function itself. That is cos of minus x is equal to cos x. Its mirror image is the same as its original signal. But in case of sine signal, this is not the case. This is the x1 of t, that is the sine of t, and x2 of t, that is the sine of minus t, is the red one. Here you can see what happens to sine signal when it is subjected to time reversal. That's why sine is an odd function and cosine is an even function. Cos of minus x is equal to cos x and sine of minus x is equal to minus sine x. Now let's do signal addition operation and get its graph. For that x1 underscore t is equal to sine of t and x2 underscore t is equal to cos of t. Let's define x3 underscore t is equal to x1 underscore t plus x2 underscore t, and in a plot function let's include x3 underscore t also. In legends function also let's include its name as x3 underscore t. Now let's run this code and obtain the graph. So we will get the graph like this. X1 of t is sine, x2 of t is cos of t, sine of t, cos of t, then it's summation. Sine of t plus cos of t is this yellow colored graph. Blue colored graph is sine of t, red colored graph is cos of t, and yellow colored graph is sine of t plus cos of t. So you can do signal addition in this way. Then let's do signal multiplication. For that we can change this plus operator to multiplication. Remember to put a dot before multiplication, because here we are using the scalar elementary multiplication. Otherwise it will do the matrix multiplication. So let's get it like this. This blue represents sine of t, red graph represents cos of t, and it's a product. This yellow is its product. In this way we can do signal multiplication. So in the production of sinusoidal signal in discrete time case, the spacing on the x-axis is more when compared to the spacing on x-axis in case of continuous time signal. And here you use the function or command stem to produce the discrete time signal. Here you use plot for getting the sinusoidal signal in continuous time case. Sinusoidal signal in discrete time case will look like this, and sinusoidal signal in continuous time case will look like this. Hope you understand the generation of sinusoidal signal in discrete time and in continuous time. Thank you for watching this video.
Hello guys, it's Muhammed Salmun here. Now, today I'm going to explain how to generate real exponential signals in Matlab. So, what are real exponential signals? Now, a real exponential signal is a signal that follows the equation x of t is equal to a e raised to sigma t. Now, that is in the case of continuous time signals, and there is also another case where the signal is discrete time signal. Now, in discrete time signal, the equation will be x of n is equal to a e raised to sigma n, where n is the time steps. Now a e raised to sigma is a constant, so which we replace by small a, and the equation becomes x of n is equal to a raised to n. Now we can get four types of signals with respect to the value of a, where a is greater than 1, a is between 0 and 1, and a is between 0 and minus 1, and a is smaller than minus 1. So let's see how the signals will be on all these four cases. Now we will move on to Matlab. So how we generate a signal in Matlab is similar to how we plot a graph in real life. We select some x points, put it in the equation f of x, and find the corresponding y points, and we just plot the graph. Here also we are doing the same, but the difference is that we can choose a wide variety of x-axis points, like a lot of x points we can take. In real life, you will be just choosing 4 or 5 and just assume the other values and draw a graph. Now here the advantage is that we can choose a lot of numbers and the MATLAB will provide us with the graph. Now I will just copy paste my code and we will explain step by step. Now the first step, as I just mentioned, is declaring the x-axis. Now the x-axis will be from -10 to +10 over in my case, and it will choose a one value step each time. That is from -10, it will just next calculate -9, and then it will calculate the point of -8 and so on up to +10. Now we are going to generate the real exponential signal with that will be a discrete time signal with a greater than 1. So I have chosen a point 1.5 which is greater than 1, and the equation will be r of n is equal to a raised to n. This will be a dot operation. This multiplication will be a dot operation, so it will be a raised to n. And I have given a title for my graph as exponential with a raised to 1. I have given the x-axis as discrete instance of n and y-axis as amplitude. Now how we plot a discrete time graph is using the function stem, which you have already familiar with. So let's see how the graph looks like. So as expected, it is a growing exponential graph which starts from -10 and ends at +10. So it's as simple as that. We have simply generated a discrete time graph of real exponential function using Matlab. Now we will look at the other cases where a is between 0 and 1, 0 less than a less than 1. So we have to choose the value of a between 0 and 1, so that I will choose as 0.5, and now my heading of the graph will be this, and the rest is same. So now we get a graph which is opposite to the first one we got. Now it is a decaying graph and it is exponential. Now we will look at the third case where a is between -1 and 0. Now so I will now set the value of a as -0.5, which is between -1 and 0. I will also change my title, and let's see how the graph looks like. So this is also a decaying graph, and it is decaying in a sinusoidal type of way. Now let's look at the fourth and the final type where a is less than -1. So I will choose that as -1.5, the value of a as -1.5. I will also change my title over here. And let's see how the graph looks like. We should be expecting a exponential growing graph. We are getting a growing graph. Before moving on to continuous time signals, I would just like to show one more thing. Now this graph we have just plotted using these equations are just points, and these points are not connected. These are just points because we got using the function stem. So how to connect these points? For that we use a function known as plot. So if we use plot, we get a signal where all those points which were marked are now connected. Now this is not not so curvy. So what happens is that they just connect these points. So when we plot continuous time signal, we need a more curvy graph. Now I will explain how we will achieve that. Before that, let's see what's the equation for continuous time signal R. Now the equation for continuous time signal as given is x of t is equal to a e raised to sigma. Now we get three types of signals depending on the value of sigma. Now a is the amplitude of the graph, which will be the point when x is t equal to 0. and we get three types of signals. That is a signal that is parallel to x-axis, that is a decaying exponential graph, and an growing exponential graph when sigma equal to 0, sigma less than 1, and sigma greater than 0. So let us plot these graphs in Matlab. Now as we can see, there are some values on the command window, so I will just clear that using the co function clear and CLC. Just run that. So let me just copy paste my code and I will explain it. Now the x-axis I have chosen as the variable t from -10 to +10, but I have chosen the value step as 0.1, so I get more number of points between -10 and 10. Now the points will be -10, -9.9, -9.8 up to 10. So I have now I have a more number of points. That means my graph will be more curvy. So that's been settled. Now the equation is that r of t is equal to a into e raised to sigma t. Now the a will be the amplitude, which is given as 10, and the sigma, for the first case we are using sigma is equal to 0. Now so I have given a variable sig equal to 0, and I have written the equation as a into e raised to, that as I have for writing e raised to in Matlab, I have used a function known as exp. Now exp inside the bracket, if anything is there, that comes as e raised to sigma into t. So the x-axis is t from -10 to 10, and the y values will be the r of t. So I have given some title, x labels and y labels. Now let's see how our graph looks. So as expected, it is a graph parallel to x-axis and the amplitude is 10, which I have given. So let's move on to the second case, where sigma is less than 0. We should be expecting a decaying exponential signal. Now it will be sigma less than 0. I would give a value as minus 0.2. It is slightly less than 0. Since it is exponential, the graph will be, the y-axis of the graph will be big if I give very big numbers over here, that we can see. Okay, now here also my title also will change. So let's see how the graph looks like. See, we have got a decaying exponential graph, and the x-axis is from -10 to +10, and the amplitude, that is when x is equal to t is equal to 0, we get 10. That is the amplitude we have given. So what if I choose a bigger number like -5, which is also less than 0? We can barely see this graph, and let's see the values of x. See, it is not 6, it is 6 into 10 raised to 22. So the graph is not so visible, and it is a very large, the exponential factor is very huge. So that's why I have chosen a smaller number. Now we will look on to the third case, where sigma is greater than 0. I will give sigma equal to 0.1. Also I will change my title. The rest is same. I will just run my code. So as expected, we get a growing exponential signal. Now where at 0 it is equal to 10. So that's all with continuous real exponential signals. Hope you guys understood. Thank you for listening.